once again. Today we will be looking at a toy example of gradient descent using PyTorch so that you can understand the concept of backpropagation. After we understand the backpropagation briefly, then we will start coding simple linear classifier using PyTorch, and then we will start coding very simple neural networks using PyTorch. Actually, we will code a network that looks like the LeNet 5 that we saw in the slides last time. So then finally, hopefully, we will be able to look at get the weights of an existing network and then adapt it to do a small task that we want, which is called transfer learning or fine tuning. So that is the plan for today. So today also I'll be doing the class for 2 hours, and then we can do the same thing on Monday night at 10 p.m. So that we can have the rest of the class. I think that's much more convenient. Okay, so if you even totally forgot what we did last time, if you just watch this, it will be sufficient. Now you can see I have given a nice curve here. This is a degree 4 function. That means it has x to the power of 4 and x to the power of 4 term. So that's why it has two minima. You can see the two minima here, one minima here, and one minimum there, and another minimum there. So depending on where you start, now here you can see I have started this dot O, my x value is 1. So now I want to follow the gradient, and hopefully I will go to the minimum. So you can see if you take the gradient here, it's a negative value because the slope is that way. It's a negative value. So therefore, we move in the opposite direction of the gradient. So negative value means negative direction means this direction. Negative means this direction. Negative is this direction. But gradient descent means we have to move in the opposite direction of the gradient. That means we will actually move in this direction. That's the thing about the gradient descent. Okay. So if you do that, hopefully we will reach the minimum after some iterations. So this is what we did when we ran these examples. You can see it goes there and sort of stays there. So you have to have some criterion of stopping this. So by the number of iterations or some other criterion, you have to stop that. But that is not a concern right now. But I think you understand by doing gradient descent, we can find the minimum of a function. This minimum should hopefully correspond to the solution that we want. Okay, that's enough to understand that gradient descent. But you can see for gradient descent to happen, we have to compute the gradient of the function. Compute the gradient of the function. Now I will show the gradient of this function. So this function hopefully you remember from your A-level mathematics. O-level mathematics to find the derivative, we did that last time. So if this my fx is equal to, we had w to the power of 4, right? Plus minus w to the power of 3 minus 12 w to the power of 2 plus 15w plus 5. Okay, this is the function that we had. Okay, so from this derivative theory, we know that d x to the power of n by dx, yeah, is equal to n x to the power of n minus 1. This is something that you must have learned. Otherwise, just it's a very simple thing, right? So now what we needed to do was we had to compute the gradient. We call it actually f prime x. F prime x. We had to compute. F prime x is equal, we called it gx in our computation. We had to compute that. And we applied that individually to each of these terms. So that we had double 4w to the power of 3, remember, n minus 1, plus, what do you get here? You have w to the power of 3 here. That means 3 comes to the front, 3 w to the power of 2. And then we have minus 12 here, and 2 comes to the front. 12 times 2 is 24 w, and plus 15. This is the gradient that we got. So you can see we manually computed the gradient. By manually computing the gradient, we were able to move a step, right? So how did we move? This motion, we had the new value of w, okay, w. If you like, you can call it t plus 1 or something, if you like. W t plus 1 or something, you can call it, equals w t, what's the thing, minus some step. We call it eta, yes. Huh? Okay, I wrote x here, that's a mistake, right? W for w. Eta FW, right? That's the thing we had. That's the gradient descent equation we had. Very simple, very simple. So now you can see, since this is manual computation of gradient, then what I told about PyTorch is, it is a PyTorch and TensorFlow. They are automatic gradient computers. They will compute the gradient automatically. But one thing is, now if this function is defined, now you can see fw is directly a function of w, but not all functions are like that, right? There's some functions are defined like function of a function kind of thing. That's how functions are defined. Function of a function. When that happens, you have to use this thing called backpropagation. That's what I'm going to do now. I have uploaded a few slides on backpropagation. Not everything. I cannot handle everything on backpropagation in this class because this is not a deep learning class. So, but I picked a few slides for you, and I will briefly talk about backpropagation. I have uploaded that set of slides also. Okay, a brief introduction to backpropagation. Okay, yeah. So if you just summarize, we must define a score function and a loss function. Okay. So that means when you give a data point to the neural network, it will produce a score, and based on that score, we have a loss. That means the image is a cat image and the output is a dog. So therefore, there's a loss. We have to quantify that loss using some function. Okay. So assume that we have, this is the function that takes the d-dimensional data. So we saw that last time d is the number of x values that you have in input, and it produces, let's say, a k-dimensional quantity, and then this input is d-dimensional. It is not a difficult thing to understand if you think about an image. For example, if you take these simple grayscale images 28 by 28, we will study that today, 28 by 28. So our d will be equal to 28 by 20. By 20. I think this is 768 or something. And that many numbers, okay? They are a little bit high. Okay, so this is k, maybe is the number of classes. Maybe if you count digits, like 10 digits, 0 to 9, okay? And this is our function. Now you can see it is not just a simple function of W, right? Because it is a little bit complicated. So we have the B2 that has to be estimated, B1 that has to be estimated, W1 that has to be estimated, W2. And X is an image, one of our images. So you can see this S or the score is a function of B2, B1, W1, and W2. And this is for a fully connected network. So I have shown this fully connected network here. This I am showing 3072 for color images, 32 by 32 color images. So if you take a 32 by 32 color image, we briefly saw that last time. So this I am showing this 32 by 32 color image. So its width is 32 pixels, the height is 32 pixels, and it's a color image. So therefore they have three channels. So that's how you get this 32 by 32 by 3, which is 3072 from 200 or 2000, something like that. Okay, now there are different kinds of losses. So SVM loss, we did SVM, but I did not talk about the SVM loss too much. So this maybe you remember the margin. This is that margin 1, and then they have softmax loss, and so on. Many loss functions can be defined, and you can get the mean square loss also. That means subtract the correct value from the uh, uh, predicted value and then get the square of that. That also can be done. Then regularization, all the things. But anyway, what you need to realize is you have a loss function which is function of W1, W2, B1, and B2. These are the parameters that we have to estimate, the neural network parameters. Then all you need to understand is this loss function's gradient with respect to W1 has to be estimated. This loss function's gradient with respect to W2 has to be estimated, and so on. Okay, I have made a mistake here. This is B2. All these things we have to be estimated. Then we can use a gradient descent. Actually, this is called stochastic gradient descent. I will explain that again today. In order to find W1, W2, B1, B2, we can optimize. Maybe sometimes you can use classical optimizer like quadrature programming in support vector machines. Or when you have many layers, we use stochastic gradient descent. For that, we need backpropagation. Okay, so let's see what that means. So need for backpropagation. So as usual, if you have any question, do not hesitate to ask me. I'll be very happy to answer. I'll be actually delighted to answer. Then the requirement is to find parameters W1 and W2 such that the loss gets minimized. We can use an optimization scheme based on gradient descent. For this, actually there's a little bit of a thing that I have to add here, W1, W2, B1 and B2, right? B2 also. We can use an optimization scheme based on gradient descent. For this, we need these gradients. This is what you need to understand. These four gradients we need. So why are we using this this symbol? DABA symbol to say partial derivative. That means we consider all other variables constant and consider only B1 as a variable. That's fine. Then we can learn W1, W2, B1 and B2. However, L is a composite function of W1. It's not a simple function like we saw before in the toy mathematical examples that we had. Computing the gradient of L with respect to W, so this is the gradient of L with respect to W, on paper is tedious. Changes, example, changes. Example, use softmax installation. If you do some change to this network, you have to recompute the gradients. So this is not feasible for complex models. Building a computational graph and using backpropagation can efficiently compute these gradients. So we will see a small computational graph and then see how backpropagation is done. First, this graph. Okay, you can see this simple function intuitively. The chain, this is called a chain rule. Okay, states that knowing the instantaneous rate of change of z relative to x, that of x relative to t allows us to calculate the instantaneous rate of change of w. Okay, mistake here. Sorry about that. Rate of change of z relative to t. Okay, so let me explain that again. So you can see z is a function of x and x is a function of t, right? So I'll show you an example later. So it is like that. So you from x you can go to z, but you cannot directly go from t to z. This is not possible. You have to go through x. Yeah. When I show you an example, you'll understand it very easily. So when this happens, the equation is this one. dz by dt is equal to dz by dx by dt. Okay, let me show you an example. Maybe you remember. Let's consider an example like that. F t is equal to 2x plus 1 to the power of 3 or something. Okay. Yeah. So how do you differentiate that? Now, what you do is you write it like that, right? You write, okay. I'm confusing you further. I can write it like that. I can write this. I use an intermediate variable x and write it as x to the power of 3, and x I can write as 2t plus 1, right? 2t plus 1. So if you slightly remember how this is done, we consider this as one block. We consider this thing as one block. This as one block. And you apply that familiar rule that you have. So remember that derivative of d by dx. So this is a different x, okay? d by dx. X to the power of n is equal to nx n minus 1, right? This rule you apply. So since we are considering this as one block, this is like x to the power of 3. So therefore you will have to have 3 this thing squared, right? And then we have to multiply that with this thing's derivative, right? Something like that. So therefore, I hope you remember, you write it like 3 2t minus 1 2t plus 1 squared multiplied by the derivative of this 2. 2t's derivative is 2, like that. So you can see here, you can see this one's derivative is 2. Yes, so this is the chain rule. So you can see directly we multiplied by, took the gradient of this one with respect to that variable we called x and multiplied by the derivative of x. Derivative of x with respect to t is 2. So dx by dt is 2. Here you can see that we can call this z by dx is 3x squared. Can you see that? You just multiply. I mean, no big deal. You just multiply. We call it the chain rule. So, simple anecdotal example is this. As put by George F. Simmons, if a car travels twice as fast as a bicycle, and the bicycle is 4 times as fast as the walking man, then the car travels 2 times 4 equals 8 times as fast as the man. Yeah. With this, you can understand that the chain rule is true. Okay. So that's the chain rule. Any questions about that? Okay, let's move forward. All right. So now, but when you have graphs slightly more complicated than that, that means, for example, to reach Z, you have 2 paths, through X and through Y. So Z is equal to XY is a function of X and Y, and X is a function of T, and Y is a function of T, like that, with G and H. So then you will have the chain rule like this. Partial derivative of Z with respect to X and dx by dt. partial derivative of z with respect to y and dx by dt, like that. So you can see the chain rule for any composite function. You can write the chain rule. In this situation, it is convenient to call this is the dependent variable and x, y are the intermediate variables and t as independent variable. So like that, you can write the chain rule. This is only an example. Yeah. So then there are many more complicated examples, but I will not talk about those things to you. Okay. Now let's take this example. What we are going to do now, right now is, okay, we are going to apply the chain rule and find the gradients of this function f with respect to x, y, and z by backpropagation. And then we are going to code that in PyTorch, and you will understand this is exactly what PyTorch does. Yeah, then you will be very happy that you understand what happens there, and you will know how neural networks generally get optimized. Okay, so are we ready? Any questions up to now? Okay, so let's move forward. Now consider this f x y z equals x plus y times z. Very simple, right? X plus y times z. What is there to think about it? But we can consider that this one as q. We consider this one as q, so that I can explain you this chain rule thing. Okay, now my q is equal to x plus y, because I put q, this is equal to qz. Okay, now take these two equations and draw the graph. How am I getting f? I am getting f by multiplying q and z. Multiplying q and z. So I have multiply node here. This multiplication node is exactly the multiplication node right here. Yeah. All right. How do you get q and q? Z dr anyways, it is there. Q is x plus y. So I have this addition node here and x and y over there. So you can see this is the computational graph. This is the computational graph. So now that we have the computational graph, if I give you the value of f and the gradient of f, I can backpropagate that. So this is what we are going to do now. Okay. So assume that in the forward pass, I take x equals -2, okay, due to some reason, y equals 5 and z equals -4. Can you take some time to, okay, you can quickly compute it by looking at this, but rather than looking at this, by looking at the computational graph, can you compute? X is -2, y is 5, and z is -4. So I will ask you a question so that you can answer, so that I know that you are understanding this. Mm. Okay, let me run this. So please answer this question. Oh, maybe you see a question on the screen. Please answer that. Oh, no one is answering. Yeah, one person answered. Two. Okay, excellent. Mhm. Six people have answered. 7. I'll give you 1 more minute. 8, 9. Oh, some are answering on the chat. That's also good. 11 people have answered. So in a short while, we'll stop this. Okay, I'm stopping. Uh, yeah, these are so many people have answered. Okay, so here's the answer. So -2, 5, and 4, and then when you can compute q. Q is equal to x plus y. So that means q will be 3 -2 plus 5. And then f is equal to 3 times -4. That means -12. The forward pass is okay. Now we'll go for the backward pass. Backward pass, we must compute the derivatives. So that means we have to compute the derivatives of okay, partial derivative of f with respect to q. With respect to q. That means we have to consider partial derivative with respect to q. All others are constants, right? Except q. Q, f is q, is it? Right? So since this z is a constant, we are differentiating with respect to, this is like differentiating 2x with respect to x. That means you will get the answer as x, 2, 2. So here is the answer is z, right? Yes. Then I need the partial derivative f with respect to z. Partial derivative f with respect to z. So the same thing, partial derivative z with respect to z. I wrote b, this partial. Then because we consider q as a constant, answer is q. So it is okay. Let's move forward, backward fast. So df by df is 1, that please remember that. And then df by dz is q, we have it here. And df by dq is, df by dq is 4, z is actually z, as you know. Z value right now is -4. Q's value right now is 3. So now you can see we are computing the partial derivative another time. Now we have the partial derivative with respect to q. -4 is there. Now we want to compute the partial derivative of f with respect to x. What is that equal to? Now we have to use the chain rule. That is equal to partial derivative of f with respect to something that we know, q. Q times partial derivative of q with respect to x. Partial derivative of f with respect to q is already available. That's from the upstream, it's available. This one, we know the function. So therefore, we can compute that. That means we know that q is equal to xy. Because we know that q is equal to xy, partial derivative of q with respect to x is equal to partial derivative of x plus y with respect to x. So what that means is y is considered a constant, so its derivative is 0. Derivative of x is equal to 1. Okay, dx by dx is 1. So therefore, you can see this turns out to be 1 and this is minus 4. So you can see this one you get minus 4. This here also you can see if you do the same computation, you will get minus 4. So now I have written all these things. If you have any question, please ask me. All these things are there. So this is minus 4, right? You can see that. That one is minus 4. Because this is the because this is the addition node. The partial derivatives turn out to be 1. That is because q is equal to x plus y. Okay, if you have any question, do not hesitate to ask. This is important knowledge. So with this, you will understand how neural networks actually do this gradient backpropagation. So now you can see after this exercise, we have all the gradients of f with respect to x, f with respect to y, and f with respect to z. So therefore, now if we have the function, f is a function of x, y, and z, all derivative of x with respect to x, with respect to y, and with respect to z are available. So now if you consider these are w's, now because we have the gradients, we can do the gradient descent. So computing the gradients of the loss function, here we consider that as f, with respect to the weight parameters is done by backpropagation. So you can see the gradients are propagating back. This one was the gradient here. This was the gradient here, 1. And then we went for this layer, and then we went for that layer. So the gradients are propagated by, that's why it's called backpropagation. So what a name, right? Backpropagation. So you can see these neural networks, some people call them black boxes and so on. They are black boxes because for them it is a black box, but not for those people who understand. Okay, so but there is a general rule for that. So if we have from the, we call it the upstream gradient, partial derivative of the loss function, whatever which is there over there with respect to z, and these are called the local gradients, the partial derivative z with respect to x and y, the input variables, and these are called downstream gradients. We compute the downstream gradients using the chain rule. So this is exactly what we did. So therefore, based on f, like whether it's a multiply node or an addition node and so on, we can define these gradients. So downstream gradient, local gradient, upstream gradient. So the downstream gradient is equal to the local stream gradient, upstream gradient times local gradient. So for example, addition node, yeah, addition node. So we saw that. If 3 and 4 are the values, when you add them, you get 7, right? That's a forward pass. If due to some reason we got the gradient of the loss function with respect to this output variable as 2, because it is the addition node, the gradients propagate, gradients get copied. That's what we saw in our previous example also, right? Because the addition node, the gradients got copied. Can you see that? This gradient got copied. That's the nature of an addition node. The gradients got copied. Yeah. For a multiplication node, the gradients actually switch. The values switch as gradients. So like that, there are rules. So using those rules, we can, so this is the add gate, and then we have the mul gate, multiplying gate. So you can see in the mul gate, so 2 times 3 is 6. That's a forward pass. If the upstream gradient turned out to be 5, this 5, to compute this, we multiply that 5 is this 3. Here we multiply this 5 with this 2. So you can see, right? So the rule for add gate, rule for mul gate, you can see, right? So therefore, depending on the node, PyTorch will know how to compute the gradient because there are rules. These are rules. So the copy gate, so there are these like that. So you can see the various, so and so on, right? And so on. And the max gate, this is the ReLU function. ReLU function, what happens, and so on. So I will not explain all these things. If someone is interested, I can explain. And we have to consider these only single variable things. So in neural network, we have vectors, matrices, and tensors getting multiplied and so on. For all these things, we had to come up with rules of how to compute and how to efficiently compute these variants. And based on those, they have implemented PyTorch. Now our exercise is take this slide, and we do the forward pass, and then we do the back gradient computation, and see whether those gradients turn out to be -4, and 3 using PyTorch. That's what we are going to do now. I hope the exercise is clear for you. So let's get about doing that. Okay, let's go to the VS Code. Give me a second to get it set up. Windows. Okay, done. I hope you are ready to do some coding now. First of all, I will get that image thing loaded. I have it saved as an image, so I will load it. That image. So I have it here as bp.jpg. Let's see whether it works. Yeah, so that's the image. So you can see like what we want are these. So let's code this. Um, uh, import torch, and then we have to define x, y, and z, right? X equals torch dot tensor. The value of the tensor is -2. We did a small crash course last time, if you remember. Require grad true. This is very important. I think you saw last time. Then it will be considered for gradient computation. Then y is equal to torch dot tensor. It's 3. It's 5. Require grad is true. And then finally, z torch tensor. Its value is 4. is Z is equal to torch tensor, its value is -4. Yeah, -2, 5, and -4. Then we have to write the forward pass. So forward pass, we write this using this Q is equal to X plus Y, and Z is equal to Q times Z. F is equal to Q times Z. Okay, so how do you compute the forward pass? So let's compute print the forward pass. Forward pass. Well, okay, it's printing the individual variables, so that's good. Let it be printed. Q and F, it's printing. So let's run this and see. Yeah. So you can see the values that we have obtained. F is equal to -12, Q is equal to 3. I mean, no big deal, okay? Q is equal to 3, F is equal to -12. I hope you're happy. Now, to do the backpropagation, should we manually compute the gradients? No, no, no. You don't have to manually compute the gradients. In the backward pass, uh, we just have to do f dot backward. The PyTorch is able to do the gradient computation with this one. So let's print this. df by dx is this one, and then df by dy is this one. df by d is this one. That's it. And you will see the gradients that we had in the slide. So -4, and 3, and -4, and -4, and 3. So you can see now what is this PyTorch doing. You give it a function, mathematical function, or a neural network, or whatever, it will construct the computational graph, I think, and then it is able to backpropagate and give us the gradients. Then we can use an optimizer to optimize the network by using gradient descent, and actually stochastic gradient descent, because we consider batches of images. Okay, so I will give you some time to code this and be happy about this. You can use any function and code and be happy about that you were able to compute the gradients using PyTorch. Okay, I hope you're happy. Now, we wanted, now let's go a little bit further, and then let's try to get the MNIST, those digits downloaded, and then we will write a little, I mean, you have to load the data. So for that, we need to write a so-called data loader and show a couple of those images, and then to train one effect, we write a function, and then we will have to write the evaluation function, and then we'll have to write the training code which we call fit the model or the training code, and then we can plot the history and so on. This code will be a little bit long, so therefore we have to spend some time in writing that. But I think it's very instructive to write this one. Um, uh, simple linear network, simple linear classifier for MNIST. Pattern. Pattern using PyTorch. Okay, let's get about doing this. Import, let's torch, of course, import to plot matplotlib.pyplot as BLT. Yeah, let's do torch import neural networks from torch, import neural networks. From torch utils data, import data load and subset. Data loader and subset. Okay. Then we have to import the datasets from torch vision. Okay, it's giving away. From torch vision. Torch vision, import datasets. Import datasets, models, transforms, and utils. And yeah, that's all we want to import. And then we'll fix the manual seed so that all of us will give every run will give the same thing. Torch dot manual seed 42 or something. NumPy also will import. That's also will seed. Yeah. Okay, importing of these packages is done. Then we have to, if you have CUDA on your machine, we have to use CUDA device equals torch.device CUDA if torch CUDA is available, otherwise CPU. To be cautious, let me put this once I don't know, is it complicated line? Okay, so I have CUDA print using device. So let me, so I have, because I have an NVIDIA GPU on my machine using device CUDA. Okay. So now when we do these neural networks or datasets, we get the mean of the whole dataset and we do some normalization with those. So this means and so on for this dataset, CIFAR10 is known. So let me do that in one cell, another cell, CIFAR10 mean. So these are standard values. So everyone knows these things, and standard deviation. Is slightly different. I have them here. Yeah. Okay. Now that's correct. All right. So now we are going to define the data loader. Def make data load, make loader. So when you're making loader, you data sets and batch size and shuffle. So when you want to shuffle or shuffle false. So return data loader, we can have the data set, batch size equals batch size, and then shuffle is equal to shuffle, and thread, uh, so number of workers, in the code that I checked, it has been 0, so I think you can increase that for sure. In memory, uh, I do not know what it is. Okay, that is done. Mhm. Okay. Mm, so a torch here. Okay. That's the data loading function. Is okay. Then we need the function to, we just show some images. There, show images, some images from this data set, images. That function is I'm writing now, images, labels, class names, mean. If you want to give a mean to this, these are default values that I'm typing. Mean means none, std equals none, and n row is equal to 8 rows or something. Okay, right. Then in that definition, we have to write mm, images. So images n row detach. Please read about these things, what they really mean. Labels, torch, windows. Okay, windows. It's done. If mean is not none and steady is not none, windows, right? Um, so uh, the mean of the mean torch tensor mean div 1311 Yes, I will not try to explain these. Standard deviation torch, standard view 1311. Images times standard deviation mean t. So this is the normalization part. Um, then we are just displaying grid utils make grid images now in row how many images, figure size 12 by 6 or something, or maybe we'll make it 16 by 3. Then plt dot imshow np dot transpose 1 2 0 0 and click 0 1. These are not so important code. Okay, you can see that this is just trying to display the images. So no big deal. Plt.be the title. Title. Last names labels. Type for I labels. I labels. Last name int I labels. That's the display helper function. So using that we can display images. We'll do it later. We'll write the other helper functions also. This is a displaying function. That's okay. Not too hard function. That one show images. But now then we have the training of the one epoch function. Def train one epoch. So you can see this is I mean complicated code than that, but this is not conceptually complicated. But oh, remove everything. Model, data loader, criterion, optimizer. Optimizer. Okay. Then model dot train running loss is 0. Something is troublesome, right? Running on the train. Running loss is 0. Correct. Set it to 0 and total to 0. Okay. For input and targets means labels in loader. So this code you have to memorize because this is again and again when you are loading data, this is what you have to do. Inputs, targets, inputs to device, target to device. Now they will be put to the GPU in my machine because my device is GPU. Then optimizer, this is a very important operation, zero gaps. So every iteration you zero the gaps. Outputs equals model dot outputs, and the loss criterion outputs target. So I will define that later, and then loss backward. So now I think you understand what this loss backward means. That one we did with this small example. And optimizer the step is a gradient update step, and then we zero the gaps. Zero the gap is not required because we have zero the gaps at the top. So let me not do that. Then we have to record this loss and so on. Running loss is equal to loss dot item times input size. Then correct ones plus equals. So in the outputs, the maximum argument 1, whether it's equal to the target, that's correct, and then we sum them. So it's slightly cumbersome code, and the total target dot size 0. Then we return from this function the running loss divided by total, correct divided by total, and we can multiply it by that 100%. Okay, that function is also correct, I think. No errors there. So now we know how to compute one epoch, one of the iterations. Then we have the evaluate function at torch dot lograd. Def evaluate model load criterion. Doing it right? Doing that? No, it's there. Oh, it typed everything. I want to go step by step. So model dot eval running loss is 0, correct 0. That's okay. These are okay. And then for inputs, now we are going to do inputs, comma targets in loader, inputs, comma targets to device. Then outputs model dot inputs, and loss criterion with the criterion outputs and targets must be given. Then same thing, running loss to title input size, and the correct ones hopefully is correct, and total input size 0, that's also correct, and then we return running loss, and all these things we return as before. This is for the evaluation part. That means we don't do backpropagation here. You can see torch get. So we have the function, the train one epoch function where we do backpropagation. Okay. Then we have the actual training part. That's the important part. Def fit model part. Then we have to model, give it a model. Then the train loader and the validation loader. Remember, we have to divide the training and the validation set, like training and testing set. Criterion, optimize and epochs. All these things will go line by line. Then we keep the history because we want to plot, do the plots and so on, history. I will upload this code after I do this, and I ensure that it is working. Train loss, train accuracy, validation loss, validation accuracy. Thinking everything is, I don't want to know that. Okay. Then things like we retain best state equals copy, not deep copy. We need to load copy. Yes, copy deep copy. So that is the best state we retain. Then best validation accuracy is 0. -1 that I do not know. For epoch. Now carefully watch this epoch in range 1 to epochs. So now we are running to all the epochs that we design. Maybe we want to do 100 of them. So we from each epoch we are running. So for one epoch code we wrote, right? Train loss, and train accuracy we can get from the train one epoch. So every time I have to erase if I hit the tab key, and I am automatically hitting the tab key. I have gotten used to it. Train loss, train accuracy, train one epoch, model, train loader, criterion optimizer. That's fine. And validation loss, evaluate model, evaluate model, evaluate model, validation loader, criterion. That's okay. Then to the history, loss, append train loss, train accuracy, append training accuracy, validation loss we append, and validation accuracy append. This is to plot. So if validation accuracy is greater than best validation accuracy, we said best validation accuracy, and best state, and we do this deep copy thing, and then we can do a bit of printing, print epochs out of the number of epochs. We can bring that in 0 to D because we don't have any large number of epochs. Epoch and then training loss we can print, and training validation accuracy also we print. Printing part is done, and then model load state, best state, and then return the history. Okay, so that part is also done. Then we can have the plot history function. This function I will copy, so let's not spend time in that. Because we have the history recorded, now we can plot it. Plot history part is this function. I hope this all the coding is fine. So now our task is to download the CIFAR10. So it will take some time for you to download the CIFAR10 dataset. It will download quite a little bit of data from the internet, and then we can display these images. So downloading data and displaying is the part that we are doing. CIFAR10 and displaying. And displaying. Okay. So CIFAR10 transform equals transform dot compose transforms to tensor transform. I'm sorry it's taking time, but I think it's important for us to go through the code of one of them. Normalize CFAR 10 mean and CFAR 10 STB. These things we defined at the top, right? Is it okay? CFAR 10 transform transform compose transform to tensor, compose transforms to sensor, transforms normalize CFAR 10 mean, CFAR 10 STB. So and I'm successfully writing down that in a markdown. You know, that part is okay. Then CFAR 10, this is the data set, train full equals data sets. Data set CFAR 10, I don't know this. Okay, just hit the tab key, so it will download into a folder called data. Training is true, download true, transform CFAR 10 with the CFAR 10 transform is the thing. So then the test one, data sets to get that. Train false, download true, that's correct. Is there a mistake here? Okay. Then class names, if are 10 full classes. Okay, so we can print the class names. Train dataset. CFA train full, we'll take a few of them, okay? Don't take everything from 0 to, because it has 50,000, I think, 12,000, because it will take time otherwise, 12,000. And then similarly, validation dataset from the CFA train full, we'll take from 12,000, 15,000. And then test dataset CFA train test, if the subset CFA train test will take about 3,000. Okay, let's see whether this is working. Okay, so these are the classes: airplane, automobile, bird, cat, deer. These are the classes in the CFA 10 dataset. Train loader, model loader, train dataset, batch size. We can take a batch size of 128 or something. That means how many images we take at a time. Shuffle through, validation loader, make loader, validation dataset. Batch size 256 or something. Shuffle, pause, batch size to reach test dataset. Is there a mistake here? Make load is not defined. So let me see. I forgot to define that. Loading function. Make load. Spelling mistake there. All right. Now we are ready to. We have loaded now, ready to get some images and print them. Images. images, labels, equals, next. So this is how you load them. Okay, so show images, we load this function. Yes, then uh, yeah, so we can show the images and see. So these are some of the ones. This I think randomly gets this and displays. I don't know how this function works. So maybe we can ask what it does. So we can maybe print the sizes of these data sets, print um, train subset size, length of the train data set. We can print, and then we can print the test subset size. Sometimes validation subset size and the test subset size, and we can print them and see. Yeah, okay, so the 12,000, 3,000, and 3,000 training set. Now we can do a simple classifier. This is the most important part, I think. Now class linear classifier, and it's inheriting from in the module. So we will not go through all the details of this, but you have to do a little bit of studying on your own. So we init that with the number of classes equals 10 for this CFAR. And then let's see the self linear, in linear, 332, 32, that's correct, and the number of classes. And forward self.x, so return self linear, we have to flatten this x equals torch dot flatten x 1, so flatten that, and then we can do a linear self dot linear and x. That's our neural network. That's a linear network. That's all. Return self dot linear. That's all. Let's run this and see whether it is okay. It is okay. Then we can we have defined the class, but it's not been instantiated. So linear model. So now we can get initialize with the linear classifier, number of classes, length, number of classes. But all these things are not required because we have put it 10 here to device. That is putting that in the GPU. Linear criterion, so-called cross entropy loss. And the linear optimizer, torch optim stochastic gradient descent, linear model parameters, learning rate 0.05 or something. I think you remember what learning rate means. Eta in our gradient descent example. Then there's a thing called momentum. Momentum is 0.9, and there's a thing called weight decay. Weight decay 10 to the power minus 4. That's okay. Momentum. Momentum. Okay. So, so now these are the things that we have to give to our fit model function. So we'll keep the history as we have defined, linear history. Fit model, this is a function that we coded before. We have to get the linear model, the train loader, the validation loader, the linear criterion, optimize, and how many epochs. So let's run about 5 epochs. That's okay. Then we have to linear test loss. Linear means because we have named it as linear, we want to linear test accuracy evaluation. We evaluate linear model, test loader, linear criterion. That's okay. Then we can print them. Print linear model test loss, linear model test accuracy. Yeah, okay. By the way, mm, linear model test accuracy, linear test loss, test accuracy is okay. By the way, what did I want to say? Mm, okay, this has 10 classes. So more than 10% accuracy is better accuracy. Okay. If the accuracy is 10%, that means random. More than 10, it's okay. So let's run this and see. Hopefully it will work. Okay, so now we can see we are running 5 epochs, epoch of 1 of 5. Train loss is 8. Accuracy is 24. Already train accuracy is good, right? It's better than 10. Validation accuracy is low. Validation accuracy is low, 24. Of course, it should be like that. So now it is slowly increasing. Sometimes it decreases. But training accuracy should improve. So you can see test loss and test accuracy. We need the test accuracy is there. Yeah, 27 point. It's not bad. So that's a linear classifier. So it just you flatten the image that to a 32 by 32 by 3 size. Yeah, and then connect that to 10. That's it. Just a linear classifier. Just it's not actual neural network. So what we did this cat example, maybe you remember something like that. So we can plot the history and so on also. For that, I will use this code here and do that plotting the history. So you can see the history is horrible. So training loss, you cannot see that. You have to run for many epochs and see. And accuracy, training accuracy is improving, validation accuracy is going like that. But I don't think we can very well interpret these. So you can see slightly the things that we wanted, like bird, slightly looking like a bird and so on, it will happen. But if you run for, I think, many epochs, maybe the images will become better. These are the templates, the weights. Okay, that part is over. Now we want to make this neural network slightly better, slightly larger, a slightly larger simple network, right? A simple neural network. So let's code that. Now, because we have spent time in writing all these functions, we can quickly get it running by writing very few lines of code. Only this much is required. So let's do that. Now we make the network a little bit larger. So class simple multi-layer perceptron, MLP. Class we studied what MLP is, simple MLP or something, MLP. Then we'll do a CNN also, nn.module. Then okay, let me see if this is okay. Super init number of classes is 10. Hidden dimension we can give. Hidden dimension 256 or something. Then super init hidden dim, and let me see carefully see this hidden dim. We connect the layer from this to hidden dim, and ReLU activation, that's fine, from hidden dim to number of classes, that's correct. Then forward, X you flatten, uh, and then ReLU you apply, then you FC2 you apply. This is fine. You can do it this way. Or you can use this the sequential one that let's do that. Self.net equals nn.sequential. Then let's do this flatten. You apply a linear one, and then this is like flatten the image. Apply a linear one from this many nodes to this many nodes, and then ReLU into number of classes, and then this is enough for that. Now it's quicker to code. Then simple MLP, simple MLP2 device, and it is the same things that we have done before. First entropy, then optimizer, torch. Okay, they have used Adam. Learning rate is yeah, weight decay. We don't need weight decay. Adam is a very powerful optimizer. Adam is the starting point of optimization. And that means the gradient descent. Simple history, simple MLP history. Fit the model simple MLP, test loader, train loader, validation loader, criterion. Okay, epochs 5, epochs 5, 5 epochs. Okay. Simple MLP loss, simple test accuracy, evaluate, and then like last time you can bring them. Plot history also. Easy enough, right? Yeah. So it will take a little bit of more time than the previous one. And accuracy should improve because we have a slightly larger network. It's a multi-layer perceptron rather than a linear network. So already the accuracy is validation accuracy is 40%, right? That's quite good, as you can see. So not too bad. So you can see when you make the network larger and larger, accuracy improves. But this is not always the case. You just cannot make networks larger and larger and larger. So you have to carefully think about those things. Okay. So let it run and plot the history. Then we'll use a we'll code now Linux. Okay, now you can see the curves are much better now. Training accuracy is reduced, training loss is reducing, validation accuracy is reducing and increasing, and training accuracy is increasing, validation accuracy is also increasing. So you have to run for more epochs in this case. So 43%, 44% accuracy, much better. So best accuracy is of course 100%. Now let's do a Linet 5 like convolutional neural network. Linet 5 like CNN or CPAT. To remind you what this is like, not exactly exactly this Maybe there will be slight differences in the code that we are doing. This is the network that we looked at, like 10F5. So let me get a screenshot and put it there so that you can, when I put the code on the display, you can quickly. This one I'll put. Save that. Okay, let me put that level 5 here. Yeah, so this is what it is. So you can see this is what we're going to code now. So see, I mean, all this peripheral code, I did not explain. I don't know some of them. I just copy them. But this part you need to understand. So in the previous network, this linear, we flatten. Flatten means that 3072 dimension or something, you flatten it to one vector, and then you connect it to, fully connect it to the number of classes, that's 10. And in this case, we have flattened it and connect to a hidden dimension, and then do a ReLU nonlinearity, and then hidden dimension to 10 number of classes. So of these, computing the total number of parameters and so on, I hope you know now. So let's do that exercise, total number of this thing after, if you have time after this, after coding this. So now one difference is like this is 32 by 32, but you know that it is not the case because we are using the color images now. So in our case, this will be 3 times 32 by 32. So all other sizes and so on, you have to be careful. They may change. We're going to load it, but that's okay. Let's code it. All right. So now our neural network level 5 like one class, the same thing, okay, with the same structure. Class Linet 5 like or something, Linet 5 like neural network inherited from innet module. I hope your Python knowledge is okay. So yeah, so here uh, def init, uh, everything it types. I want to just hit and get some completion. It types everything. So for init, that's okay. These things that we did previously. Then self dot features and then sequential. Okay, now let's see how you do this. In neural network con 2D. First of all, okay, these are 2D cons, con 2Ds. 3, 6, kernel size 5, side 1, padding 2. I hope you remember these things. We studied them last time. So 3 input channels and 6 kernels. I want to load this correct image, then I can show you again and again. I don't know why that. Even if I want to load, it's not loading. I don't know whether I have to restart the kernel for this. Let me see it as a different one. Okay, so this is what we are doing. So you can see it's 3 channels to 6. That the 6 is correct. So now you can see that this is okay. Then after that, you know that we have to put value activation in dot value. That's okay. I think then after that, you know that max pooling happens to make it 40. They did not do max pooling, but we will use max pooling. Stride to kernel size 2. Then after that, another convolution layer. How many kernels? 16 kernels. And con 2D, 6 to 16, kernel size is 5, stride is 1. Then a ReLU, then again max pooling, kernel size is 2, stride is 2. Then after that, what do you do? Then after the max pooling, okay, convolutions are there. 2 cons, con 1, con 2, and ReLU max pool. Max pooling is fine. And after that max pooling, we will have this one. That one we connect to 120, right? Uh, um, okay, let's have another one for that. And then classifier, we call it the classifier. The search feature computer part is okay. Flatten that, okay. Flatten that, okay. Let me do it. Flatten that. And then linear classifier from 16 by 16 by 5 to 120. Linear layer, linear layer. 16 by 16 to, I hope these numbers will be correct. 120, 120 to 84. Remember 124, 84 to 10. 84 to 10. ReLU. Is putting value correct. Correct means, I mean, is it faithful to, that's okay, let's do that. Okay, so now it is okay. Now let's define the forward one, get the X, you forward kept with the features, get X, and put the features in the classifier and then return this. This is fine. And then what we have to do is we have to initial create an object, len it 5 like, this is the object, len it 5 like 2 device. The same thing, len it 5 like 2 device. 2 device. And len it criterion we need, cross entropy, len it optimizer, Adam, learning rate, we make it slightly larger. Maybe. Oh, no, yes, okay. Optimizer, len it 5 criterion, len it 5 optimizer. Okay. Then history and so on, you have to identify history, fit model, identify like train loader, validation loader, criterion, optimize the ethics, and then the train loss, identify like test loader criterion, and then we printing thing and so on. Let me hit the tab key and get them. I hope that's okay. So now let's run this and see. This is a convolution and neural network, something like this. Only difference is here we have three channels rather than one, and we have used ReLU. Oh, let by history, let waves cannot be multiplied. Problem here. Fine. Model F5 line, train loader, validation loader, make fighting. Okay. Not a problem. Hmm. I don't think I'll be able to resolve this right now. Hundred twenty 500, 400 by 120. Then we put it from the 16. Put the sizes 3 to 6. We choose this one is as 6 times 5 times 5 times 5 times 5. Let me check again. The size problem is from here. Two by 32. Because we are not hmm, because this doesn't become 28 by 28, I think, because we have not said we have added padding here. That's the problem. We remove the padding also. Yeah, now it's working. Uh, so remember this, it automatically added padding. So in the Lenet 5, there is no padding. So that's why, as you remember last time from 32 becomes 28. So that was a mistake I made. It automatically added padding here. Padding means it retains the, right? So you already you can see the accuracies are improving. So maybe 50% something like accuracy. Uh, Okay, that's okay. So now you can see this one. So I'll give you the file. I know a little bit, I'm going a little bit fast. You have no time to code this, I think. Um, uh, but I need to do one little more example. Is that long? Then I'll copy some parts of the code and then rest I will do. Sorry about that because we had run out of time. Yeah, so you got about 50% accuracy. That's good, right? Did we write 10 epochs? Yeah, I forgot to change that. And cannot start the coding. Okay, so you can see it's quite good, right? Validation accuracy. It's also improving. Um, so now we want to do this fine tuning pre-trained RESTnet or another dataset. This is the usual way to do get neural networks working. We don't train from scratch. So previously we trained from scratch. ResNet 18. I will talk about ResNet on Monday. Dataset, another dataset. Uh, so okay, so unfortunately, one part of the code I will have to copy. Uh, so ResNet weights default, ResNet process, ResNet weights transform, ResNet process mean, ResNet standard deviation. Transform 224, 224, normalize. Okay. So CFA 10, we don't have to download again. It may download. Subsetting. Yeah, all the things that you can understand except the first one. So ResNet. For that, we need to import. We need to have. This we forgot. We have to get ResNet weights from Torch Vision. So ResNet is a neural network that has been invented in 2016. It's user 15. So that we are going to use to do a task that we do another task. Okay. So um, I'll write few bits of code and then ResNet 18 models ResNet 18 weights ResNet weights. So this is the thing that we have to do. We are getting the ResNet weights. ResNet weights. Okay, you can see model ResNet weights, ResNet weights. So these weights we download for around in ResNet parameters. Can you see that now we don't let it train? The ResNet we don't train. It's frozen by making this all the parameters false. So num features equals ResNet 18 features. Then ResNet. Okay, now it's an important line now. ResNet 18 FC in the linear num features to 100. Okay, so this is the new layer. ResNet 18, ResNet 82 device. Let us be putting in the GPU. ResNet criterion, cross entropy. ResNet optimizer, Adam optimizer. This is fine. Then we'll do the same thing. So remember, we have taken ResNet's parameters. This is the head optimizer, because we are only optimizing this last layer that we added, this one, last layer that we added. And then this is, I think, familiar to you. So then we can fine tune other parts also, other parts of the ResNet also. Training only the new classification head, as you can see, and we are running only 2 epochs, as you can see here. So this data set is called CIFA 100, that has 100 classes. Their sizes are different. So through this transform, the sizing changes, and then you can see number 100 classes is the output number of nodes. Yeah, so now it's being trained. So you can see ResNet has been trained on something. Okay, they are trained on 224 by 224 color images. These are very different. CIFA, until it trains, I will briefly show you CIFA 100 dataset. So this all these things are done by this Alex Krzyzewski and so on. So see, this is the CIFA 10 dataset. Then the CIFA 100 dataset. So they have that many classes. So CIFA, this dataset is just like CIFA 10, except 100 classes containing 600 images each. There are 500 training images and 100 testing images per class. The 100 classes in CIFA 100 are grounded into 20 superclasses and so on. So you can see beaver, dolphin, otter, those are the classes, different kinds of classes, camel, cattle, those are the classes. So it will take a little bit of time. But that's also, but only thing that you need to understand is, the most important thing that you need to understand is, we are using ResNet existing weights. These weights we are downloading from Torch Vision. These networks have been trained by someone. So Torch Vision has networks that have been trained and the weights are trained. So we are getting them, and now we do not want to fine tune or change the weights of everything of ResNet. So we are changing the weights of the final linear classifier that we had. So this 200 resize transform will take the CIFA 10 images and resize them. And then dataset has been loaded here. So you can see the transform is in there, so that it will do the resizing there of the image. And then you can see we have model ResNet 18, weights, ResNet weights. And then we say for all the parameters in ResNet, we say requires get false. That means it will not train. So then number of features we compute by we extract in this one, and then ResNet 18FC neural network layer number of features 200. This fully connected one we connect that one, we train that last layer. So this number of features, let me see how many are there. So you can see accuracy is good. Cannot run. Okay, so that's all we want to talk about today. So what we looked at today was we looked at gradient descent again, and then we looked at how uh, for gradient descent we need the gradients. Gradients of the loss function with respect to the weights that we want to optimize. So therefore we understood what backpropagation means. Backpropagation is computing the gradients of the loss function with respect to those weights. Then with that, what we did was we manually computed the gradients, and then we got PyTorch to compute those gradients. Now you understand what backpropagation means, and we understood what gradient descent means. Then we did a simple linear classifier for CFA10, and there we don't have to manually compute the gradients, and we just have to say forward, and then it will know how to compute the gradients in the backward pass. But we wrote quite a bit of functions so that to help us to get this working. In that, the important function is the train one epoch function. There you do the uh, loss dot backward you do. Loss dot backward you do. This is the most important line. And then optimizers dot step means you are updating the gradients. And then optimizer is not actually gradient descent, but you can use a stochastic gradient descent. But Adam is optimizer that you have to use. It will make your life so much easier. Then we enlarged the network size little by little. We had a few more layers, one or two more layers. It's a multi-layer perceptron. After the multi-layer perceptron, we did a CFA10-like structure, and the accuracy improved. There you can see, and then finally we started fine-tuning a pre-trained ResNet on another network by freezing all the parameters, but by adding a final linear layer, a final densely connected layer. Yes. So that's all. So as the time is up, we will conclude the class. So I will be available for any questions, of course, as usual, for some time. And we will meet on Monday at 10 p.m. also. That also I will record and upload so that you can get some practical experience on these neural networks. Okay, thank you. If you do not have any questions, you may log off. Otherwise, you can stay in the class and ask. Thank you very much for participating in the class, everyone, on a Saturday. Questions? Yeah, thank you, everyone.